Focus. All right, electron configuration is the easy way. So when we go to do electron configurations, yes, this is take. Electron configuration is the easy way. How do we do electron configurations? Well, anybody ever play that game Candyland? You ever play Candyland? Where do you start in Candyland? At the start. Start at start. So when we go to start electron configurations, here's where we always start. Because the electrons, we start the ones closest to the nucleus, and we always build up. So it's a natural progression. So start at the start. Second thing we do is we go left to right, then we drop down to the next level. Kind of like when you guys are texting. When you go from one side to the other, until I get to the very end, then I can drop down to the next level. When we write out electron configurations, imagine you're in a hot air balloon floating over Boca, and you're looking at the different neighborhoods in Boca. You have, like, let's say this is Broken Sound, this is Woodfield, this is Colonnade, Estancia, all those different places, right? When you look at them, the way you want to think of it is every neighborhood has a different street number. So if you notice here, the first thing I notice is these are 1 through 7, and P is basically 2 through 6. It kind of matches exactly. The S and the P match. The street numbering that doesn't match is in the D neighborhoods. It goes 3rd Street, 4th Street, 5th Street, 6th Street, and then finally in the F neighborhood, it's 4th Street, 5th Street. So when you look at it, that's the way you want to look at it. Then I write street is my energy level. I was just showing you the streets. Hood refers to the neighborhood, whatever neighborhood it's in. Then we use a letter to designate that. Houses on that street, how many houses over are you? That's all you have to do when you do electron configurations. Now, to remember the blocks, all you have to remember is smart people don't forget. So when you look right here, it goes smart people don't forget. Now, when we go to do a couple electron configurations, watch, I'll start with the easy one. Let's start with the hydrogen right here, or helium. Helium is right there. Where do I start? At the start. I'm going to be right here. What street am I on? I'm on 1st Street. So I write street. What neighborhood am I in? S. And then how many houses over am I? So the electron configuration for helium is 1s2. That's the electron configuration for helium. If I wanted to do another one, let's say I want to do the electron configuration for beryllium. I still start here, which means I have to go through hydrogen and helium, which is represented by 1s2, 1st Street, S neighborhood, 2 houses. Now what street am I on? 2nd Street. I'm on 2nd Street. What neighborhood am I in? S. How many houses am I going to go past to get to beryllium? I'm going to go past 2. So the electron configuration for beryllium is 1s2, 2s2. So now what I want you to do is on a piece of paper, but you guys won't do it on a piece of paper. You guys are going to do it on a whiteboard, but they'll do it on a piece of paper, is I'm going to give you one to do, and I want you to try it. So what I'm going to have you do is I want you to write out what you think the electron configuration for nitrogen is. Take a minute, and then I'm going to hit pause, and we'll see what we get. So, good. The electron configuration for nitrogen. Here's nitrogen. Here we go. When we go to do nitrogen, we're going to go through this. This is represented by 1s2. Drop down. I got 2s2 here. And then finally, this is 2. P neighborhood, 1, 2, 3 houses over. So the ultimate electron configuration, the final electron configuration is 1s2, 2s2, 2p3. Represents nitrogen. The next one I want you to do is I'm going to pick iron. So Fe right there on the periodic table. So what I want you to do is I'm going to hit pause, take like 30 seconds, write out the electron configuration on the paper, and then we'll go over the answer. All right, so when we go to do the electron configuration for iron, we start here. This is going to be represented by 1s2. Drop down here, 2s2, then we go across here. That is the 2nd Street in the P neighborhood. There's 6 houses I go by. This is going to represent 3s2. This is represented by 3p6. This is 4s2. Finally, when I enter in this neighborhood, this is the D neighborhood, but remember the street numbering is different. This is 3rd Street. The 1st street here is 3rd Street, 4th, 5th, and 6th. So this comes out to be 3, the D neighborhood, and then 1, 2, 3, 4, 5, 6 houses over. So my electron configuration for iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6 is the correct configuration. All right, let's try a longer one. Let's try, do you remember how to do a noble gas shortcut? The way you go to do a noble gas shortcut, here's what you do. If you don't want to write it all the way out, what you do is you basically can go to the noble gas on the previous line. Noble gas on whatever the period above the element you're doing is. So go to the noble gas on period above, and then what you do is you write it in brackets. So I write brackets, and I want to write the symbol for the noble gas, and then all I have to do is just the last line. So all I'm doing is the last line of the electron configuration. So, por ejemplo, let's say I wanted to do the electron configuration for Te. So I want to do the electron configuration for Te. It's in this period. I can go to the period above and grab that noble gas, and all I have to do is the last line after that. So what I'm going to do is I'm going to hit pause, take about 30 seconds, write out your electron configuration using the noble gas shortcut, and we'll see what we get. All right, so when we go to use the noble gas, so when we go to use the noble gas configuration, here's what happens. What we do is we're trying to do Te. We start at, we're allowed to go to the period above the noble gas, which is going to be krypton. So I'm going to write Kr in brackets, and all I'm responsible now for is writing the last line of the electron configuration. This represents 5s right here, so this is 5s. Remember, this section is 4d, so this is 4d10, and then finally this would represent, this is 5p here, so this would be 5p 1, 2, 3, 4 houses over, and that represents a electron configuration for Te. Now, one of the other things we do is we draw orbital diagrams. Orbital diagrams. Someone's holding up a sign saying the 49ers are criminals, and yes, they lead the National League Football League in arrests, but that hurts. When you go to draw an electron diagram, all you're doing is representing the electrons with arrows. So here's what it looks like. For example, key thing to remember is every s orbital, every s is equal to 1 box. Every p is equal to 3 boxes when you do it. Every d is equal to 5 boxes. And every f is equal to 7 boxes. Well, what does that mean? 1 box is an orbital that holds electrons. So when you go to do a orbital notation, someone held up a sign. Aaron Riskman, Jim Harbaugh's not going to Michigan. That makes me sad. I'll cry on the way home. All right, so let's say we're going to do one for nitrogen. If I write out the electron configuration for nitrogen, it's 1s2, 2s2, 2p3. Let's say I want to do an orbital diagram for it. When I go to do an orbital diagram, what I would do is I'm going to make a little box here. Every s is equal to a box. So I have 2 boxes right there. They're not the same size. Then when I go to do p, I know that p is represented by 3 boxes. So I'm going to do this. So when I go to convert this into an orbital diagram, I'm going to do this. My 1s, this would represent my 1s orbital. Every s is 1 box. Every p is 3, so this is my 2p orbital. There are rules for the way the electrons fall in. There's rules that state that electrons have to be opposite each other in the orbitals. That is the Pauli exclusion principle. Remember that from last year. If not, the Pauli exclusion principle means that you cannot have 2 arrows going the same direction. So that's muy mal. That's Spanish for bad. You can't have more than 2 electrons in a box. And then there's something called Hund's rule. Does anyone remember what Hund's rule is? Yes. In a section, you can't start pairing electrons together until you put an electron in every box. So when I go to do this, this represents, I can fix it, this represents right here 2 electrons I have to put in the s box. So I put 1 arrow up, 1 arrow down. In the 2s orbital, I have 2 electrons, 1 up, 1 down. Finally, I have to put 3 arrows in, or 3 electrons in. When I distribute them following Hund's rule, I go 1 up, 1 up, 1 up. That is the correct electron configuration for nitrogen. Okay? So now what I want you to do is I want you to write out here's what we're going to do. I want you to write out the electron configuration for sulfur. So you write it out and then draw it out. So the top line, you write it out. The second line, you're going to draw it out. So I'm going to give you, I don't know, take a minute. I'm going to hit pause. So hit pause, take a minute, and then write out the electron configuration for sulfur, and then draw it out using the boxes. Ready, set, pause. All right. So if you go to write out, I'm going to do it on this one. If you go to write out the electron configuration for sulfur, sulfur is 1s2, 2s2, 2p6, 3s2, 3p4 is the electron configuration for sulfur. So that's the electron configuration for sulfur. Now, when you go to put it into its boxes, I'm going to need to add a couple more boxes here. Let me do this. And then let me do this. And add a couple lines here. So ultimately, here we go. I'm going to convert this into an orbital diagram. How many electrons in the first one? 1 up, 1 down. Second one, 1 up, 1 down. 6. I go 1, 2, 3, 4, 5, 6. 2, 1 up, 1 down. Oh, this is all I didn't label this. 1s, 2s, 2p. This is 3s, and then this is 3p. I have 4 electrons to distribute. I have to use the rules. So I go 1 up, 1 up, 1 up, following Hund's rule. You're not allowed to pair the electrons until everyone is filled. Why do I put the electron there and there instead of putting the electron there? Why does it have to go there? Why? Electrons always want to be as low as possible. And it's following the other 2 rules. It's called the off-bow principle. It's just like, let's say, for example, Aaron, you call a radio station and you win a contest. You want a ticket to a Justin Bieber concert. You have 3 choices. Hold on. Don't answer for him. If you want the tickets, you can either take row 1 tickets, row 3, or row 5. What row would you pick? 5. Wrong answer. You're not supposed to take the tickets. You're supposed to reject that. But anyway, ideally on this case. Ideally, though, the way it works is you want to always be as close as possible, right? So this electron, rather than distributing when you go to pair them up, you distribute the electron here versus there or there. And then that's exactly how you do an orbital diagram. And that's my favorite player. That's it. I've had it. I've stopped recording.